I'm going to assume that most of you have heard of OLED, mostly known as that fancy screen technology used in phones and TVs. You might even know that OLED is short for organic LED, but what is organic about it, and what does that even mean? That's what this video is about. How OLED works, even at the molecular level, and how it compares to other screen technologies like LCD. In terms of functionality, I'm sure a lot of you know that OLED has an advantage because each individual pixel is its own light source. Unlike LCD panels that have an LED backlight, then block light of different colors using liquid crystals, only passing through colors you want. If you want to know more about how LCDs work, you can check out my other video where I talked about dead pixels, but I also went into heavy detail about how the panel technology works as well. But the basic difference is that LCD selectively blocks light, where OLED selectively produces light. But to really understand what's going on with OLED, first we need to know about regular LEDs, or light-emitting diodes. A diode is an electrical component that mostly just allows electrical current to pass through it in one direction, or in more scientific terms, it has low resistance in one direction and high resistance in the other. This is useful for converting alternating current to DC current, for example, because it effectively cuts off or blocks half of the waveform when it reverses, but that's all beyond the point of this video. Anyway, a light-emitting diode is just a diode that emits light when electricity passes through it. No surprise there. With a typical LED, the actual light emitting part of it is made of a semiconductor die, which is just a little small cutout piece of a semiconductor wafer, very similar to how CPUs are cut from large wafers. Then you just hook up some wires to the semiconductor piece and it can make light. On the other hand, OLEDs are actually really different, both in what they're made of and their manufacturing process. You see, OLEDs are made of organic compounds. Okay, but what does that mean? Well, an organic compound is simply any chemical compound or molecule that contains carbon-hydrogen bonds. Obviously, that's pretty general, and there are literally millions of these compounds known, and they're very common. And organic compounds are called that because all known life is based on these types of molecules. So in the context of OLED, organic doesn't mean that it uses materials harvested from plants or something, just that it uses similar molecules also found in living things. But that doesn't mean that every organic compound is necessarily found in life, because there are synthetic organic compounds that are technically organic from the definition, but are purely man-made and don't exist in nature. There are still a lot of questions we have though, like how do OLEDs work at the atomic level? What causes them to burn in? Why do they use organic molecules anyway? But don't worry, I'm going to explain all that. Okay, so to explain how OLED works in the first place, I am going to have to get into some physics. It's pretty complicated stuff normally, but I'll do my best to simplify it and make it easy to understand based on how I understand it myself. Admittedly, I'm not an expert on this stuff, so don't hate me if I make some small errors or leave something out. You can, of course, let me know down in the comments if I do. All right, so you might remember from school that atoms have layers of electrons surrounding them called shells, and how each shell has different levels of energy depending on how close they are to the nucleus. You may also remember that electrons can actually be shared between atoms, for example with covalent bonds. However, electrons can also be what is known as delocalized, which means that they're not really closely associated or stuck with any atom in particular. So if you have a crystal lattice, basically a organized structure of many molecules near each other, these molecules may sort of share electrons and pass them around. These are also called free electrons and are often a big factor in how electrically conductive a material is. All right, so now we have some context, but what does that have to do with OLED? Well, everything. You see, molecules used in OLED are special because they emit light when a current is passed through them. How this happens is when current passes through them, it adds energy which is absorbed by those molecules and their electrons. This extra energy kicks some electrons into a higher energy layer of the electron shells, known as the conduction layer. When this happens, this leaves an electron hole in the lower energy level, or the valence shell, where the electron was. Simple enough. There is a lot more physics on this bit than I could possibly get into right now, but if you want, you can get more details if you look up the Wikipedia page for excitons, which is the name for this combination of an electron and electron hole. Anyway, eventually this excited state of the outer electron decays, and the electron falls back down from the higher energy level to the lower energy level, filling the hole. and in doing so, releases its extra energy in the form of a photon, or light. This is called recombination, and the color of the photon emitted depends on how much energy is released, which in turn depends on the molecule or the material. Now, over time, OLED panels are known to degrade and potentially burn in. What causes that? Well, in the recombination process that we just mentioned, it doesn't always produce a photon. When it does release a photon like we want, it's called radiative recombination. But there can also be non-radiative recombination, where the energy from the electron falling back down is released in other ways. For example, the energy may be transferred to another electron in the form of heat. Or if there is a defect in the crystalline structure in that part of the panel, like that little pixel, there may be an extra energy band that the electron can fall into, so it doesn't release enough energy to make a photon. One form of non-radiative recombination is known as Auger recombination, which is believed to be the main cause of degradation in OLED. Basically, there is a very small chance for an electron to collide with another atom's electrons and cause it to have such a high energy level that it actually breaks an atomic bond completely. This is called homolytic dissociation and results in atoms or fragments of molecules being separated into what are called radicals, which basically end up being defects in the structure of the panel at the molecular level. The more of these radicals, the more they interfere with the electrons around them, causing even more kinds of non-radiative recombination. Therefore, this ends up decreasing the efficiency of the panels over time. So why use organic molecules at all? Why not use regular inorganic LEDs? Well, we do, but only for huge displays, and it comes down to the difficulty of manufacturing LEDs at very small sizes. Typically, LEDs are individually made components, each cut from a piece of semiconductor, so they have to be constructed and placed on a panel one by one. Even for a 1080p screen, that's 2 million pixels, which will take a long time to make. And then you have to remember it's actually all RGB subpixels, so really it's 3 times that. You also have to have a way to wire up all these LEDs, and there's just a ton of room for error. Now, like I said, for massive panels like those used on billboards or something, they are viewed from very far away. So the LEDs don't have to be very small or close together, so it's easy to make them. But the smaller the screen, the harder it is to pack individual LEDs together as pixels, so it's better to use other technologies like LCD at these high pixel densities. So what is it about how OLEDs are manufactured that make them able to overcome this issue? Well, OLEDs are manufactured completely differently than regular LEDs. In fact, OLED pixels aren't really made of a physical diode with wires and stuff at all. You see, with an LED, you have to cut from a wafer, like I said, and wire it up to pass current through it. Organic molecules, from my understanding, are a lot easier to manipulate though, so instead of using wires to pass current through them, you can just take one conductive sheet, spray OLED molecules onto it, and then sandwich it between another conductive sheet. Then what you can do is energize those 2 sheets, and depending on how big they are, they could even be the size of a single pixel, and it just energizes all the molecules between them at once so it all lights up. In other words, OLED can be deposited as a film between 2 layers which act as anode and cathode, and whatever parts of that film get power will light up. This means you can have squares of OLEDs, for example, that are not really an individual point of light, but rather an entire square that can light up uniformly. Now, to make individual pixels, you just have to find a way to divide up the anode and cathode layers so it can provide voltage to only a tiny certain part of the screen at once. So to make a pixel, you can create what is called a matrix of anode and cathode layers, which is basically a big mesh that lets you choose and energize individual points, one for each pixel. Then you can deposit the OLED material onto the matrix in each spot. And you'll also probably need a way to control which types of OLED molecules you put where, because different molecules emit different colors of light. This can be done in a number of ways, including literally inkjet printing on each pixel, so you can control exactly where each type of molecule is deposited. Or you can put the OLED material into a gas form, from my understanding, and then vacuum deposit it so it's uniformly distributed. Of course, remember, the way I'm explaining it is very oversimplified. Anyway, the main takeaway is that OLED is manufactured in a completely different way from LEDs that is way easier than if you wanted to make tiny regular LEDs of the same size as OLED subpixels. That being said though, you may have heard about micro LED, which I have mentioned on this channel before, and it's basically the holy grail of display technology. Micro LED refers to screens that do actually use traditional organic LEDs being used as individual pixel elements, just like with OLED. If these elements could be shrunk down to what is necessary for, say, a TV or monitor, it would have all the same benefits as OLED, such as not needing a backlight and having perfect black levels as a result, but it would also have none of the degrading properties of OLED. However, microLED is still not here yet. Companies like Samsung and LG have made microLED TVs, but they have to be huge, like 100 inches plus, because the LEDs are still relatively big, therefore the pixel density is not nearly as good as LCD or OLED. Also, because they are tough to manufacture and it's new technology, they are extremely expensive. However, these companies are obviously working on methods to improve and shrink the LEDs and improve the speed of making them. I personally think eventually microLED will replace OLED, but it will take several years. Now, you may be wondering more about these organic compounds that are actually used in OLED, and there are several of them used depending on the tech. The current two major types of OLED technology either in use or in development are known as small molecule and polymers. But for some context, at least in 2019, by then, basically all OLEDs were still the small molecule type. In this context, small molecule basically just means a carbon-containing molecule that is literally relatively small, specifically having a molecular weight under about 1,000 or so. On the other hand, polymers are very large molecules formed as long chains, but I'll get to them later. One example of a small molecule used in OLED is, well, this name, abbreviated as ALQ3. This molecule contains aluminum and carbon and is known as an organometallic chelate. That's not really important, but it just sounds cool. Here, the aluminum is in the middle, and it's surrounded by three branches of a group of molecules known as 8-hydroxyquinoline. According to a 2006 scientific paper, this organic compound is special because by modifying and substituting certain atoms in it, you can tune the frequency of light emitted, so it can be used to create various colors spanning the entire visible spectrum. In simpler terms, you can use it to make lots of different colored pixels. That is just one example of a molecule used in some OLED though. There are lots of other potential small molecules. The other type of technology we can talk about is called either PLED or POLED and uses light-emitting polymers or LEPs. A polymer is a general term for typically very large molecules with repeating subunits. So basically a big molecule with a repeating pattern forming a chain. For example, DNA is a polymer, along with nylon, silicone, rubber, and lots else you probably see every day. Anyway, POLED uses a type of polymer called electroluminescent conductive polymers, which is fancy talk for an organic polymer that lights up when charged with electricity. Apparently, by substituting different so-called side chains on the molecule, you can determine what color it lights up as. Here are some specific polymers used for different colors. There's polyphenylene, which is a blue emitter, polyp-phenylene-vinylene, it's a green emitter, and polyalkylthiophene, and it's a red emitter. You can see these little diagrams show the base pattern, and the brackets indicate that it repeats on either side. All that being said though, like I mentioned, my understanding is that polymer-based OLED is still mostly in the development stage. Finally, there is a third possible type of OLED that is still being explored called phosphorescent OLED or PHOLED. These would work on the principle of phosphorescence, which I'm not going to get into because it would require even more physics I'm not prepared to explain. But a major benefit of this type of OLED would be that it is way more efficient than other forms of OLED. Again though, this is apparently still pretty early in the research phase. So by now, you should be an OLED expert and probably learned way more than you'll ever need, but hopefully found it interesting. So let me know down in the comments what you thought. If you guys want to keep watching, the next video I'd recommend is the one where I was talking about actual causes of dead and stuck pixels on LCD monitors and possible ways to fix them. You can just click that right there. So be sure to subscribe if you found this interesting, and thanks for watching guys. I'll see you in the next video.